This video is on magnetic force and motion in magnetic fields. Question 1. Compare the following equations of force: Newton's law of gravitation, Coulomb's law, and the magnetic force. So, which force equations look similar to each other, and what do they have in common? Well, the force of gravity and the electric force look similar because they both have a constant, g and k, and both are proportional to 1 over r squared. Which force equations look different from each other? What do they not have in common? Well, the magnetic force looks different because it has that cross sign, that multiply sign, and a velocity component. There's no velocity component in the force of gravity and electric force. Question 2. List some differences between the electric force and the magnetic force. Okay, so a stationary particle can feel an electric field and therefore an electric force. A stationary particle cannot feel a magnetic field and therefore it cannot feel a magnetic force. The electric field and therefore the electric force can make a charged object speed up or slow down or change direction. The magnetic field and therefore the magnetic force can make a moving charged object change direction only. The kinetic energy of a moving charged object will not change when it enters a region of an external magnetic field. The magnetic field and therefore the magnetic force cannot make a charged object speed up or slow down. Question 3. What are the units and the fundamental units for the magnetic field B? Well, let's go back to the original problem, number 1, and solve for the magnetic field, which is B. So, simplifying, we get kilograms over amperes second squared. And the units of the magnetic field is Tesla. Question 4. Use the equation magnetic force equals QV cross magnetic field external with the right hand rule to find the direction of the magnetic force of the charged object. So here are their steps. Take out your right hand, put your fingers from your right hand in the direction of QV. Step 2, bend your fingers in the direction of the external magnetic field. Step 3, your thumb points in the direction of the magnetic force. And note, if the charged object has a negative charge, then just switch the direction of the answer. Okay. So we're always referring back to this equation. Part A, proton is at rest. A magnetic field with constant magnitude points to the right. Okay. So the proton is at rest. So look at this equation, QV cross B. If V is 0, then magnetic force is 0. Part B, a proton moves to the right with a constant speed. A magnetic field with constant magnitude points to the right. Okay. So remember, put your right hand and your fingers in the direction of QV, which is to the right. Bend it in the direction of B. Well, you can't bend it because B is in the same direction as V. Okay? So the sign of 0 is 0. That's why there's no magnetic force. Part C, a proton moves up with a constant speed V. A magnetic field with constant magnitude points to the right. So put your fingers up from your right hand in the direction of QV. Bend your fingers to the right, which is the direction of the external magnetic field, and your thumb points into the page. Part D, a proton moves into the page with a constant speed v. Now point your fingers in your right hand into the page and bend your fingers to the right because the external magnetic field is to the right and your thumb points down. So the magnetic field, the direction of the proton is going to be down. Part E, a proton moves out of the page with a constant speed of velocity. So point your fingers in your right hand out of the page towards you, towards your eyes, and bend your fingers to the right because the external magnetic field is to the right, and your thumb points up. So the proton moves up. Part F, a proton moves down with a constant speed v. So your fingers in your right hand point down. Your fingers in your right hand are going to bend towards you, and your thumb is to the left. So this proton is going to move in a circle towards the left. Part G, QV points down, B points into the page. So your palm is going to face away from you. Now when you bend your fingers away from you, your thumb points to the right. So pause the video, try to solve for H. Now pause the video and solve for I. Pause the video, solve for J. Pause the video, solve for K. Pause the video, solve for L. Pause the video, solve for M. Pause the video, solve for N. Pause the video, solve for O. Pause the video, solve for P. Pause the video, solve for Q. Pause the video, solve for R. Pause the video, solve for S. Question 5. A proton is moving horizontally to the right. It enters a region between a uniform external electric field as shown below. Which direction should the external magnetic field point if the proton is to move to the right without deflection? So, we just want this proton to move to the right. We know the electric field is going to point downwards because the electric field points from positive charge to negative charge. So the electric field is going to make this proton go down. So we want the magnetic field to point up. So we have to use guess and check. And if there's a magnetic field pointing into the page, then the magnetic field points up. So the fingers from your right hand point to the right, because QV is to the right. If the magnetic field is into the page, then our fingers bend into the page and our thumb is up. So the magnetic field is into the page. Question 6, same situation. We want this proton to go down without deflection. We know electric field lines point from positive charge to negative charge. So this proton is going to be pushed to the right from the electric force. Now let's talk about the magnetic force. We want the magnetic force to go to the left, so we have to use guess and check. So if the external magnetic field points out of the page, then the magnetic force is to the left. Question 7. Determine an equation for the charge to mass ratio for a charged particle entering a uniform magnetic field. The velocity of the charged particle is perpendicular to the external magnetic field. So imagine a positively charged particle moving up with a magnetic field pointing out of the page. So F equals ma equals mv squared over r equals qvb sine of 90, which is just qvb. And just solve for q over m. Question 8. Use the equation magnetic force equals IL cross B and the right-hand rule to determine if parallel wires with current moving in the same direction will attract or repel. So you need to use two versions of the right-hand rule. Just memorize that two currents moving in the same direction will attract each other. Question 9. Use the equation and the right-hand rule to determine if parallel wires with current moving in opposite directions will attract or repel. So just memorize that two currents moving in the opposite direction will repel each other. Question 10. Describe the equation F is equal to BIL sine theta for a current carrying wire. So the magnitude and direction of the force on a current carrying conductor in a magnetic field is given by this equation. So if the current carrying wire is parallel to the external magnetic field, then the current carrying wire will experience no force, because the sign of 0 is 0. And if the current carrying wire is perpendicular to the external magnetic field, then the current carrying wire will experience a maximum force, because the sign of 90 is 1. Question 11. A proton is moving with a velocity of 820 meters per second through a magnetic field which has a field intensity of 1.2 Tesla. Assume that this proton is moving at right angles to the field. Part A. What will be the magnitude of the resultant magnetic force? Use the equation QVB sine theta. Part B. What will be the force on the proton if the direction of motion of the proton is parallel to the direction of the magnetic field lines? Sine of 0 is 0. Question 12. A magnetic field which has an intensity of 0.950 Tesla is directed vertically downward. An electron is moving horizontally through the field from left to right with a speed of 1.2 times 10 to the 4 meters per second. What will be the direction of the magnetic force acting on this electron? Part A. Here's the solution. Part B, describe the path of motion of this electron as it moves through the magnetic field. It's going to move in a circle. Part C, what will be the magnitude of this magnetic force acting on this electron? Use the equation QVB sine theta. Part D, what will be the radius of the circle in which this electron will move? Solve for R. A proton is moving with a velocity of 2.1 times 10 to the 4 meters per second through a uniform magnetic field, such that the proton moves in a circular path, which has a radius of 4.50 centimeters. What is the strength of the magnetic field B sub external? So just solve for B. Question 14, an alpha particle is moving with a velocity of 2 times 10 to the 4 meters per second through a uniform magnetic field, which has a strength of 2.2 Tesla at right angles to the field. What will be the magnitude of the resulting magnetic force? So we need to know that an alpha particle is a helium nucleus. It has 2 protons, 2 neutrons, and 0 electrons. Question 15, a positively charged particle moves through an area of space where both an electric field and a magnetic field are present. The two fields are mutually perpendicular and the velocity of the positively charged particle is moving perpendicular into the page, such that the charged particle passes through the fields undeflected. What is the velocity of the positively charged particle? So we're going to use this equation here. Question 16, a magnetic field has a strength of 0.78 Tesla. A positive charged particle of 1.2 microcoulombs enters the field from the top of the page with a velocity of 550 meters per second. Part A, what will be the direction of the resulting magnetic force? F is equal to QVB. So it's going to be into the page. Part B, what will be the magnitude of the magnetic force acting on this positive particle? It's going to be using the equation QVB sine theta. Part C, what will be the direction of the force of the charge on the particle is negative? And just flip the answer, which is going to be out of the page. What will be the direction of the magnetic force if the negatively charged particle is moving from left to right? Sine of minus 180 is 0. Question 17. A doubly ionized gold atom is moving in a circular path in a uniform magnetic field. The radius of the path is 12.8 centimeters and the gold atom is moving with a velocity of 6.5 times 10 to the 5 meters over second. What is the strength of the required magnetic field B? So we're given charge and we're given the mass. So we'll use the equation F sub b equals ma equals mv squared over r equals qvb sine theta, and solve for b. Question 18. A piece of wire 15 centimeters long has a current of 3.1 amperes flowing through it and is sitting in a uniform magnetic field which has an intensity of 0.45 Tesla. The wire is orientated perpendicularly to the magnetic field. What will be the magnitude of the resulting magnetic force? Use the equation BIL sine theta. What's the direction? It's going to be into the page. Question 19. A conventional current of 5.3 amperes is flowing through a wire orientated perpendicularly to a magnetic field. The strength of the magnetic field is B equals 0.6 Tesla, and the length of the wire sitting in the magnetic field is 40 centimeters. Part A will be the magnitude of the resulting magnetic force. Use the equation BIL sine theta. Part B will be the direction of the resulting magnetic force into the page. Part C, how can this wire be orientated so that it will feel no magnetic force? Let the current flow parallel or anti-parallel to the external magnetic field. Question 20 here. A wire 30 centimeters long is sitting in a uniform magnetic field. The strength of the magnetic field is 0.220 Tesla, and the current of 3.25 amperes is flowing through the wire. The wire is orientated at an angle 38 degrees relative to the magnetic field. So here's the solutions for part A and B. Here's question 21. Here's the solution for part A. Here's the solution for part B. Here's the solution for part C. Here's question 22. Here's the solution for A and the solution for B. This is question number 23. Here's the solution for A. Here's the solution for B. This is question number 24.